that in the presence of the bath, the energy levels of the system will be shifted. This part is what we would have studied in quantum 2. That's perturbation theory. When you put an interaction, you shift the energies. And that's true even if the bath were at 0 temperature, because of the vacuum fluctuations, we'll end up with lamp shifts. But in addition, there's a black body shift in the problem. But that, we can absorb into a slight change in the energy levels of the system. That's not the most interesting part to us right now. Although interestingly, I was just at GILA, in Boulder, the CU NIST Joint Institute, and I was learning that what ultimately really limits, being able to push their atomic clock precision measurements to the level now that they have 18 digits of accuracy was limited by the black body shift. And in order to get from 17 digits to 18 digits, they had to basically have a thermometer inside the vacuum chamber to know what the temperature was, so that they could calculate what the black body shift was. So, but we're talking at that level, so typically we don't worry about that. But if you're worried about 17 digits of accuracy, then you got to worry about it. All right, but this is the key here, that the correlation function is delta correlated. And that was related to the fact that the spectrum of vacuum fluctuations is effectively right. And the correlation function is the inverse Fourier transform of the spectrum of this. And that spectrum is so broad that effectively it has 0 temporal correlations. And that's the Markov approximation. Okay? And we have, and this is, and bar here is the Planck energy spectrum. Okay, so that's where we were. And what that led us to and again, I should emphasize that this relationship between the correlation of the fluctuating reservoir and the factor out front here tells us how strong is this delta function, what's the area under the curve. This relationship that we see here is an example of what we call the fluctuation dissipation theorem, which it's not really a theorem, but it's a relation that we'll return to next lecture, next week, that tells us that the characteristics of the system, that is to say, the way the system responds to the reservoir, are determined by this correlation function, which gives rise to fluctuations in the system as well as dissipation. They're all related to one another. This was first discussed by Einstein in the context of Brownian motion. And that's where these ideas, all of these ideas of system-reservoir coupling and dissipation really were discussed first in the context of Brownian motion. And what we see here is really just a generalization of that. So much of the language we borrow from the language of Brownian motion. And we'll talk about that next time. But let us continue with here. So let me just bring up my notes, and we'll continue. Okay. Anybody have any questions? All right. So, what we have thus is the master equation for two-level atom in a thermal bath. And the master equation, if we go back to the Schrodinger picture, so now I won't denote, this state is the state of the atom. Has the following form. And this is in the Lindblad form with two Lindblad operators. One associated with emission of photons from the atom into the bath, and that is proportional to sigma minus. And then there is another Lindblad operator having to do with absorption of photons from the thermal reservoir into the atom. Okay? All right. Now, and this is the Hamiltonian for the atom, which can include black body shifts and back shifts or whatever other shifts are perturbed, how the atomic energy levels are perturbed. Now, one thing that I want to mention here, which is a subtle point that is often not discussed but is important and sometimes confused, is the following. Now, when we talked about this kind of thing last semester, we also included the atom laser coupling. So we had an atom laser Hamiltonian where this was some classical field, right? And this then was, of the form, for example, the Rabi frequency of the laser, sigma plus, sigma minus, right? Or we wrote this down. And we just add this in and say this is the form of the master equation that we had that allowed us to, for example, derive the optical Bloch equations and all of the decay of the Rabi oscillations on the Bloch sphere. So the question you might ask yourself is that fair? Can I just add this Hamiltonian into the problem? I mean, shouldn't I have, re-derived this from the start by first having this as part of the Hamiltonian, and when I go to the interaction picture, then I have to include that as part of the transformation, then do that whole rigmarole with, you know, the correlation functions. I mean, how can I just, at the end of the day, just add this Hamiltonian in without thinking about its effect on the derivation of this? What do you think?
Yeah, I mean, it seems like it should have to come from somewhere. I mean, if you can't justify it through some sort of rigorous means, I don't know.
So it's so obviously this is an approximation, but is it a good approximation? I mean, in what way would adding this Hamiltonian into the system affect this part of the derivation?
Does it have to do with the difference of the Rabi frequency of the laser and then the decay of the atom?
Well, for sure, it has to do with some time scales, right? But we could certainly make the Rabi frequency of the laser comparable or even bigger than gamma. So if that's what mattered, this would certainly not be a good approximation in general. But you're right that it has something to do with some time scales in the problem. And the real question comes down to this. In what way does the application of the laser field affect the correlation of the system to the reservoir? Okay? So, because everything as we described, the whole final results that we get for the system reservoir evolution are governed by this correlation function. And the question is, how would this correlation function be different if I went to, if I include an additional interaction of the system with something else? So what we have here is the system. We have the system coupling to the environment, and then we have some other coupling to some other driving. Well, so what could possibly happen by adding this additional driving interaction that couples to the system? Well, if that driver, in this case, they're both electromagnetic in nature, right? So if the driving field had quantum fluctuations or some fluctuations that modified the fluctuation, the nature of the fluctuations seen by the system due to its coupling to the environment, that can mess things up because that affects these correlation functions. And the other question is whether over the course of the coarse graining that we do, if in any way the driver is acting on a time scale that is short or comparable to the correlation time between the system and the reservoir, well then, the system will be coupled to the reservoir or the environment in a way differently than if there was no driver. So those are two things that will, if my driving force affects that in some way, then that will certainly make a difference. In this particular context, though, neither of those things are a problem. Firstly, well, I've treated the laser field classically. opposed to a quantum field. Now, was that okay? Well, that was okay, as we discussed last semester, in the context where the laser is a coherent state. And if the laser is a coherent state, then I can make the model of transformation displace back to the vacuum. And the quantum fluctuations that are seen by that, it's just vacuum fluctuations plus a mean field. And the mean field is here, but the vacuum fluctuations are just the same as this. So that changes nothing. So that's good. But now we then have to ask the question about the Rabi frequency. And what's important here is that, so this is, if the Rabi frequency is much, much shorter than the rate at which the system and the environment are being coupled, which is this correlation time. Okay? So that is to say, if the correlation time is tiny compared to the Rabi Rabi period, well then I don't change the Markov approximation. I don't in any way affect this correlation function. And that correlation time is what in the context of the atom interacting with the vacuum?
Is it the amount of time it takes light to cross the atom or
Yeah,
something like that?
basically that's it. I mean, that's maybe an exaggeration if we really wanted to, because that's sort of well beyond the rotating wave approximation and so forth. But it's certainly no bigger, if you look at the rotating wave approximation, than the optical period. So you might say the time, an optical period is kind of the correlation. You know, it's certainly no bigger than that. And my laser Rabi frequency, again, is always tiny compared to the optical frequency. It's not 10 to the 15 hertz. Maybe it's megahertz, but it's not 10 to the 15 hertz. So, you know, the fact that I'm Rabi flopping this atom in no way affects the correlation. It's not gamma that matters. It's not gamma, it's the correlation time, which is much, much shorter. So when we have this separation of time scales, we don't have to go back and rederive the master equation. It's only if the driving force in any way changes the fluctuations with the environment, or it has a dynamical time scale that is extremely fast compared to the possible correlation time. Now, just as a little aside, this is why I don't understand D-wave computer at all. Because the whole, if you look at, if somebody can figure this out someday, I would be delighted to talk to you about this. You know, because the idea, if you look in the whole D-wave quantum computing story, it's that, well, we have to rederive the coupling of the bath to our, in the context of adiabatic evolution. And they go back and go through, you know, a kind of derivation like the one we did. It's not quite a Born approximation, I mean a Markov approximation, but it's a similar kind of scheme. And I just don't have a clue why the driving through the dynamical evolution, which is equivalent to adding a driving force here, should in any way affect the coupling to the reservoir. It seems like they're totally different scales. But it's the whole story about how they say their system works. So anyway, it's a little aside there. All right, so we could add that in. For the moment, let's just look at the problem like this. And let's remind ourselves of some of the features that come from this master equation. Oh, I guess there was one other point I wanted to make before. What if I immersed the atom not in I was driving it with a coherent state? What if I was driving it with a squeeze state? Would that change anything?
Yeah, I mean, it should, because just heuristically, your vacuum fluctuations then are different than, your original derivations.
Indeed you are. So the decay of an atom in a squeeze state is in principle, yes, could be different. And you have to really go back and re-examine that. In practice, however, it's extremely difficult to see that modification. And the reason is that the squeezing that one achieves, say, is very narrow band. It's only squeezed over an extremely narrow range of frequencies. Whereas the vacuum fluctuations are extremely broadband. They're the same fluctuations at all these different frequencies. So, I mean, people back in the 80s, when I was a small tyke in grad school and even before, we're trying to observe and trying to study the modification of spontaneous emission of a two-level atom in a squeezed vacuum, but it's extremely hard to do. You do it inside a cavity where you're modifying over some small bandwidth, but it's extremely difficult. But in principle, that's a situation where you do have to worry about it because you are modifying. So if you have non-classical driving light, then you do have to think about the rederivation of the matter equation in that context. Okay, so, right, so let's look now at this, this problem, and let's remind ourselves of some of the features. Let's rewrite this in a slightly more compact manner. Okay, so sigma minus is the outer product of that sort, and sigma plus is this outer product. And so my master equation, I'm going to rewrite this in a slightly more compact form. Okay, it comes from plugging in that first term there, and then I have similarly right?
Equal sign.
Yes, they are not equal. Okay, so let's look at firstly the rate of change of populations in this system. So if I look at, for example, let's look at the rate of change of population in the excited state. Right, that's that diagonal matrix element. So that's going to be, I get two terms over here. And then I get this term over here. Right? And that's just the rate equation. What we see here is, if this is the excited state, this is the ground state, there are different processes. There's a process whereby I can have spontaneous emission at rate gamma from excited to ground state. I can have stimulated emission, stimulated by the black body photons from the excited state. And I can have absorption of black body photons, right? Where the stimulated and absorption rates actually are equal, given by n bar number of photons at that temperature at the atomic resonance frequency times gamma. Okay, and bless you. And those are the processes that give rise to this decay rate. Similarly, it's easy to check that this is equal to this, so that the total, this is a trace preserving map, the total population in the atom preserved. That is to say, the population in the ground state is just equal to 1 minus the population in the excited state. And what we see here is
F
equals 0.
Yeah.
yeah, sorry. Thank you. So what we see here is the approach to equilibrium. In steady state, the population is no longer changing. And in steady state, thus, we have that the ratio of the population in the excited state to the ground state is equal to the mean number of photons in the thermal bath at that frequency divided by that plus 1, which is equal to e to the minus h bar omega of the atom over the temperature of the bath, which is what we expect. This is the Boltzmann factor. So when I have my two-level atom, no matter what superposition it started in steady state, it becomes a thermal state. It becomes a mixed state, and it becomes a thermal state. A thermal state with a distribution of populations that's given by the Boltzmann distribution associated with the temperature of the bath in which it is in contact. So that's satisfying. That's what you would expect. You take a system, you put it in contact with a thermal reservoir, it comes to thermal equilibrium with the same distribution. Of course, Einstein sort of did this in reverse. The whole Einstein A-B coefficients were derived in the context of the notion that, yes, the atom would come to equilibrium with the black body radiation, and in order to do so, there had to be these rates. And that's where he derived stimulated and spontaneous emission in order to ensure that this works true. But we can do it now from first principles. Right. I guess the other point to remind you of, well, I guess I should, yeah, again, of course, if the temperature is 0, it all goes to the ground state. So that's the 0 temperature limit. The coherences I look at the rate of change there, that's equal to minus I difference. That comes from this term. Remember, this is equal to the z, say. Right, that gives us that term. And then we have this other stuff, okay? And so what do we get there? Well, we get minus a half gamma n bar plus 1 times rho EG. That's from the first guy over here. Okay. This term contributes nothing. And then we have this term minus a half n bar EG again. Okay. So this is equal to or two of these. So as you remember, this is what we called the, this is the decay part, sorry. Minus I. This decay rate of the off-diagonal element is what we call the T2 time. So you recall the T2 time is the decay time of coherences. And in the absence of any other direct dephasing mechanism, this rate is just 1/2 the rate of decay of the excited state plus the decay rate of the ground state. So if I have no collisions with, say, background gas, or something which would give me a elastic collision that would dephase this, if what I have is a amplitude damping, then that gives me this kind of T2. When n bar is 0, then T2 is determined only by spontaneous emission. All right? And so we have in this problem that we just get the exponential decay of coherences. Yeah.
If I may go back to a question that I asked last time. So here we get a thermal distribution in a preferred basis, the EG basis, while apparently this preferred basis is it's originated in our choice of the Lindblad operators. So why but we could change the Lindblad operators and then we get a thermal distribution in a different basis?
No.
So how is that?
Yeah. To think about that a little bit more deeply, I don't have this completely clear in my mind, but let me tell you what is the case. Obviously, the steady state distribution is the steady state distribution. That's not a basis dependent expression. So what?
It is a basis.
No, it is not. This thing is diagonal. At the end of the day, I have a particular density operator. The density operator is an operator that is independent of the basis I choose.
Yes.
Okay, I'm not saying about the Lindblad operator, I'm talking about the basis of the atom. Okay?
Yeah.
So no matter what, at the end of the day, the steady state density operator atom is that, period. Okay?
Yeah.
Now, how it got there and how we divide that up is there's some matter of interpretation. Okay? Now, it is true that, and this is where I'm not completely clear, not the thing that I'll come back to this a little bit later, is that as you, I think, correctly say, the fact that it ended up being diagonal in a particular basis, in this case, the basis of the atom.
That's what I mean by basis.
Yeah, you know,
it's diagonal in the given basis.
Basis of the atom. I mean, it turned out to be that way.
Yeah.
Is the question is, how is it related to the choice of Lindblad operators? Because as we have alluded to and haven't really derived, there are an infinite number of master equations one can choose that give rise to the same Lindblad operators that give rise to the same master equation. And I don't have a completely clear answer to that, because we're going to see an example of a particular sense in which I mean, I think what is independent of a choice is the nature of the system reservoir coupling. And I believe that is what ultimately determines this. So, you know, we had our interaction Hamiltonian of this form, that we had this reservoir operator. In this case, I guess we called it F, sigma plus. And that ultimately set these as special operators. But where I'm not 100% clear on this, and I'll think about it a little bit more for the future, is when we ultimately get a master equation, and if we were to look at different choice of Lindblad operators, which give the same master equation, what must happen is, what happens in that case is the division between refeeding versus decay is arbitrary. How that ultimately, that division comes into this discussion, that I'm not clear on.
So in some sense, this is a convenient representation such that we'll get directly the basis or something.
Yeah, I mean, it is certainly the most natural basis, the one that comes out. We could change that. I think basis is the wrong term. It's the particular choice of Lindblad operators, right?
Yeah.
And we can do a unitary remixing, and we will. But
eventually we'll
but of course that doesn't. It's the same master equation, and when it ultimately you get to the same steady state regardless of your choice. What is different is the division between what we're calling the refeeding part and what we're calling the decay part. And that will have implications in this discussion of the quantum trajectories. But there's one point in that that I'm not 100% clear on, and that's why I'm hedging for a moment. We'll come back to it a little bit later. Okay, good. Okay, what I want to turn our attention to now is another example. And that is the decay of a simple harmonic oscillator. Pretty much those are the only two problems we care about. Orbital atom and simple harmonic oscillator. We can do a similar, the standard physical context in which we think about this is the decay of a mode of a cavity. So we have our oscillator is some particular mode, let's say the fundamental mode of the cavity, okay? That is described by a quantum simple harmonic oscillator. It could be a Fock state, it could be a coherent state, it could be a squeeze state, it could be a Schrödinger cat state, what have you. Of course, this is not infinite lifetime inside the cavity. In particular, one of the things that can happen is that even if these mirrors were perfectly passive, they had no gain or loss in them, there's only a finite reflectivity and the photon can leak out of the cavity. And that will, if we have energy in the cavity, lead to dissipation or decay of energy that was inside to outside the cavity. And an extremely important problem for us for quantum optics is to describe the quantum dynamics of the system, including the possible loss. And that loss could also be due to absorption. I mean, that's going to be depending how good the cavity is. And the mirrors are whether you lose photons due to absorption or loss. But let's really, as a simple model, we can treat it solely as due to loss. Of course, if there is thermal radiation out here, we can also have light leaking in or leaking out. Let's say this is a perfect mirror, and this is imperfect. Okay, so we can also have thermal radiation coming in if there is some at that temperature, the black body. So this kind of problem, again, we can treat as a kind of system reservoir where our system is the cavity mode. And that's its Hamiltonian. I'm sorry, not the interaction. This is the total Hamiltonian. This is the system Hamiltonian. And treat the reservoir as all the modes of the electromagnetic field, these traveling wave modes that are incident on this mirror. That can either be transmitted in or decay out, okay? So there's a kind of sum over k, again, h bar omega k, or I'll call them B. These are all the bath modes. And then we have some kind of interaction that in the rotating wave approximation, again, I can annihilate a photon from the cavity and create one in the bath, or annihilate one from the bath and create it in the cavity with some coupling constant. So it's a very similar kind of thing that we had before, but instead of having sigma plus and sigma minus, we have A dagger. Okay? And again, we can take the bath to be in a thermal state and go through exactly the same derivation, and we're going to get exactly the same kind of master equation. And when we do the master equation from Born-Markov has, again, the same kind of form. We have the Hamiltonian part, which is this, and again, the energy levels of the system will be shifted due to their coupling to the outside modes that will slightly shift the modes of the cavity. And then we have, just as we had before, I'll kappa. So this is the master equation, very important master equation in quantum optics that describes the damping of a simple harmonic oscillator. Once again, we have two Lindblad operators. That in the presence of the bath, the energy levels of the system will be shifted. This part is what we would have studied in quantum 2. That's perturbation theory. When you put an interaction, you shift the energies. And that's true even if the bath were at 0 temperature, because of the vacuum fluctuations, we'll end up with lamp shifts. But in addition, there's a black body shift in the problem. But that, we can absorb into a slight change in the energy levels of the system. That's not the most interesting part to us right now. Although interestingly, I was just at GILA, in Boulder, the CU NIST Joint Institute, and I was learning that what ultimately really limits, being able to push their atomic clock precision measurements to the level now that they have 18 digits of accuracy was limited by the black body shift. And in order to get from 17 digits to 18 digits, they had to basically have a thermometer inside the vacuum chamber to know what the temperature was, so that they could calculate what the black body shift was. So, but we're talking at that level, so typically we don't worry about that. But if you worry about 17 digits of accuracy, then you got to worry about it. All right, but this is the key here, that the correlation function is delta correlated. And that was related to the fact that the spectrum of vacuum fluctuations is effectively right. And the correlation function is the inverse Fourier transform of the spectrum of this. And that spectrum is so broad that effectively it has 0 temporal correlations. And that's the Markov approximation. Okay? And we have, and this is, n bar here is the Planck energy spectrum. Plural. Okay, so that's where we were. And what that led us to and again, I should emphasize that this relationship between the correlation of the fluctuating reservoir and the all right. So what we have thus is the master equation for two-level atom in the thermal go back to the Schrodinger picture. So now I won't denote, this state is the state of the atom. Has the following form. And this is in the Lindblad form. With two Lindblad operators. One associated with emission of photons from the atom into the bath, and that is proportional to sigma minus. And then there is another Lindblad operator having to do with absorption of photons from the thermal reservoir into the atom. Okay? All right. Now, and this is the Hamiltonian for the atom, which can include black body shifts and back shifts or whatever other shifts are perturbed, how the atomic energy levels are perturbed. Now, one thing that I want to mention here, which is a subtle point that is often not discussed but is important and sometimes confused, is the following. Now, when we talked about this kind of thing last semester, we also included the atom laser coupling. Factor out front here tells us how strong is this delta function, what's the area under the curve. This relationship that we see here is an example of what we call the fluctuation dissipation theorem, which it's not really a theorem, but it's a relation that we'll return to next lecture, next week, that tells us that the characteristics of the system, that is to say, the way the system responds to the reservoir, are determined by this correlation function, which gives rise to fluctuations in the system as well as dissipation. They're all related to one another. This was first discussed by Einstein in the context of Brownian motion. And that's where these ideas, all of these ideas of system-reservoir coupling and dissipation really were discussed first in the context of Brownian motion. And what we see here is really just a generalization of that. So much of the language we borrow from the language of Brownian motion. And we'll talk about that next time. But let us continue with right here. So let me just bring up my notes, and we'll continue. Okay. Anybody have any questions?